In 1941, inside the Clan Foundry in Belper, a team of Rolls-Royce engineers committed what looked like aviation heresy. They took a Merlin aircraft engine, the 27-liter V12 that was keeping Britain alive in the sky, and stripped it of its supercharger. They did not want it to fly. They wanted to see if the heart of a Spitfire could survive being buried in steel and mud. This was the birth of the Rolls-Royce Meteor. By 1943, this re-engineered, industrialized variant was dropped into the hull of the Cromwell tank, suddenly giving British armor 600 horsepower. It was a leap so massive that it permanently changed the speed of ground warfare. But to build it in the thousands without breaking the supply of aircraft engines, Rolls-Royce had to hand the Meteor's production over to Rover, sacrificing their own design to shadow factories in the Midlands. For the crews operating those Cromwells, and later the legendary Cold War Centurions, the Meteor was a revelation. It offered a deafening, torque-heavy roar that meant mechanical trust. But for the mechanics and logistics networks, it demanded vast supply chains of high-octane petrol, forcing an aviation drinking habit onto a heavy ground fleet. The paradox of the Meteor is that the most famous engine block in British history had to be stripped of its high-altitude elegance to become the country's greatest armored workhorse. It was a masterpiece of aviation precision, forced to act like a brutal tractor. But the real story of the Meteor is not only how a Spitfire engine went to war on the ground. It is the story of how an Aero engine became a heavy industrial servant, only to be left behind when the logic of military power finally demanded a different kind of fuel. Every week, we tell the stories of forgotten British engines, factories, and the industrial names that once taught the country what power sounded like and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place at the Belper drafting boards in 1941. In the early years of the Second World War, the British Army had a desperate mechanical problem. While the Royal Air Force was securing the skies with some of the most advanced aviation engineering on Earth, British armored divisions were dragging themselves across the ground with power units that belonged to a different era. To move 30 tons of steel through thick mud, over trenches and across broken European terrain required immense reliable power. Britain did not have it. In 1940 and 1941, the standard solution for heavy British cruiser tanks was the Nuffield Liberty engine. The Liberty was a 27-liter V12, a 12-cylinder engine with cylinders arranged in two banks in a V-shape, but it was essentially a mechanical relic. It was an aviation design dating back to the First World War, hurriedly adapted for ground use. It was notoriously unreliable, prone to overheating and structurally fragile under heavy loads. Other attempts to power tanks involved coupling standard commercial bus engines together, creating heavy, complicated systems that struggled to produce the necessary force. British tank crews found themselves entering combat in machines that were underpowered, sluggish, and dangerously outmaneuvered. The problem was not a lack of British engineering talent. The problem was industrial priority. Every ounce of high-grade material, every skilled draftsman, and every advanced machine shop in the country was dedicated to the aviation effort. This was the reality W.A. Robotham faced. Robotham was the chief engineer of the chassis division at Rolls-Royce. With the outbreak of war, the production of luxury passenger cars at the company's Derby headquarters had abruptly stopped. Robotham and his team of automotive engineers were relocated to the Clan Foundry in Belper, a small industrial town just north of Derby. They were searching for a way to contribute to the war effort that did not interfere with the sacred production of aircraft engines. Robotham observed the dire state of British tank propulsion and realized something fundamental. A heavy tank needed around 600 horsepower to become a truly fast, formidable weapon. No existing British commercial engine could reach that number without tearing itself apart. Yet just a few miles away at Derby, Rolls-Royce was mass-producing a machine that could generate over 1,000 horsepower without breaking a sweat. The Merlin. The Merlin was the pride of British aviation. It was an Aero engine, an engine built for aircraft use, where power, weight, reliability, and certification mattered differently from road vehicles. In a British hangar, the Merlin decided whether a fighter could climb to 20,000 feet to intercept a bomber. But it was built like a watch. It used expensive aviation-grade aluminum alloys. It required hundreds of hours of precision machining. It relied on a complex supercharger, a mechanically driven device that forces more air into the engine to maintain power in the thin, freezing air of high altitudes. Robotham knew he could not simply drop a standard Merlin into a tank, but he also knew he did not need to. A tank did not fly at 20,000 feet. It operated at sea level, choking on dust, sand, and exhaust fumes. It did not need a highly tuned supercharger. What it needed was torque, the twisting force, felt as the pulling strength of an engine that could rip a 30-ton steel hull out of a ditch. In late 1941, inside the drafting rooms and workshops of the Clan Foundry, Robotham's team began to systematically strip the aviation prestige away from the Merlin. They sourced crashed, damaged Merlin blocks from salvage yards, engines that had been recovered from downed aircraft and were deemed mathematically unfit for flight. They removed the supercharger, which was unnecessary at ground level, and consumed vital power just to turn. Without the supercharger, the engine could run on lower-grade pool petrol, rather than the rare high-octane aviation fuel required by fighter squadrons. They redesigned the internal structure to be manufactured from cheaper, heavier materials. The block and other major components, originally cast from precious aluminum alloys, were re-engineered to use cast iron and lower-grade commercial steel. Cast iron was heavy, but in a heavily armored vehicle, a little extra engine weight was irrelevant. What mattered was that iron could be cast in ordinary foundries across the Midlands, completely bypassing the highly specialized aviation supply chain. The displacement, the total volume swept by the pistons inside the cylinders, remained massive at 27 liters. But the identity of the machine had completely changed. It was no longer a high-strung thoroughbred. It was a brutal, heavy-breathing workhorse. They called it the Meteor. When the first experimental Meteor prototype was installed in a modified tank chassis, the results shocked the military establishment. Driven onto a test track, the Meteor-powered prototype accelerated with a violence that no British tank crew had ever experienced. It easily produced 600 horsepower. It transformed the vehicle from a sluggish pillbox into a fast, aggressive weapon. For the first time, a British tank had more power than it strictly needed. The Ministry of Supply immediately recognized the Meteor as the salvation of the British armored program. They wanted it in mass production immediately. But this success triggered a profound industrial conflict. Ernest Hives, the formidable head of Rolls-Royce, drew a hard line. He recognized the brilliance of Robotham's work at Belper, but his absolute priority was the Royal Air Force. Hives declared that Rolls-Royce would not sacrifice a single hour of machining time, a single casting, or a single skilled worker from the Merlin aviation program to build tank engines. The Meteor was a Rolls-Royce design, but Rolls-Royce simply did not have the factory capacity to build it in the vast numbers the Army demanded. The prototype proved that the block could survive the dirt. Britain now had to figure out how to build it in the thousands without stopping the aircraft that were keeping the country alive. To make the heart of a Spitfire work in the mud, it was not enough to simply remove the supercharger and cast the block in iron. The Meteor had to physically interface with the crude, heavy reality of armored vehicles, and the engineering challenges were immediate and severe. The first major hurdle was direction. An aviation propeller spun in one direction, but standard British tank gearboxes were designed to receive power spinning the opposite way. W.A. Robotham's engineers at Belper had to reverse the rotation of the entire engine. The crankshaft, the rotating, heavily forged shaft that turns the up and down motion of the pistons into rotational power, had to be redesigned so the Meteor could drive the tank forward without tearing the transmission apart. Then came the inescapable problem of heat. At 20,000 feet, an aero engine is bathed in a freezing, high-speed slipstream that naturally carries heat away from the block. In a tank, the engine is entombed in a heavily armored, unventilated steel box, crawling at a walking pace while generating immense friction under load. The cooling system, the network of radiators, fans, and water jackets designed to regulate the block's temperature, had to be massively uprated. Rolls-Royce engineers fitted large, mechanically driven fans that roared almost as loudly as the exhaust itself, sucking vast quantities of dirty, dust-filled air through the rear decks just to keep the cast-iron block from melting down in the middle of a battlefield. By late 1942, the engineering breakthrough was complete. The Meteor prototype worked brilliantly, but the industrial problem remained entirely unsolved. Ernest Hives at Rolls-Royce steadfastly refused to let tank engines disrupt the sacred Merlin production lines. The Ministry of Supply was desperate. They needed thousands of Meteors, and Rolls-Royce could only offer a trickle, assembled in a piecemeal fashion without dedicated factory space. The solution came through one of the most famous industrial exchanges in British manufacturing history. At the time, the Rover Company was working on a highly secret government project, the early jet engine, a gas turbine that produces thrust by compressing air, mixing it with fuel, and accelerating the high-speed exhaust gases out of the rear. Rover's engineers, operating out of Barnoldswick, were struggling to make the jet engine reliable, and their working relationship with its brilliant but difficult inventor, Frank Whittle, had completely broken down. Hives, seeing the long-term future of aviation in the jet, arranged a meeting with Spencer Wilkes, the managing director of Rover. According to corporate lore, they met at a local inn and simply traded their national responsibilities. Rolls-Royce would take over the complex high-altitude jet engine project. In exchange, Rover would take total control of the Meteor tank engine. The most important heavy power unit in British armored history was formally handed over to a car manufacturer. Production immediately shifted to Rover's massive shadow factory at a Cox Green in Birmingham, supported by a secondary plant in Nottingham. The aviation masterpiece was now completely in the hands of the Midlands motor industry, backed by a sprawling network of local foundries and machine shops. At a Cox Green, Rover transformed the Meteor from a bespoke Rolls-Royce experiment into an industrial commodity. They established machining lines capable of churning out heavy, durable V12s by the thousands. They simplified the fuel delivery. The carburetor, a device that mixes liquid fuel and air before the mixture enters the engine cylinders, no longer needed to function while flying upside down under negative G-forces. It only needed to survive violent jolts, deep mud, and the concussive shock of the tank's own main gun firing. The workforce at Rover adapted brilliantly to the task. They were not building the jeweled, high-tolerance aluminum blocks of the Merlin, but they were building a machine of immense mechanical integrity. The Meteor retained the 27-liter displacement and the 4-valve per-cylinder overhead cam layout, an engine design with the camshaft located above the combustion chambers, allowing the engine to breathe deeply and produce massive power. Rover proved that British mass manufacturing could take an elite, complex design and domesticate it for the brutal realities of the ground. The true breakthrough for the user, the British tank crew, arrived in 1943, when the Rover-built Meteor was finally mated to the A-27 Cromwell tank. For years, British crews had suffered in underpowered machines, creeping cautiously across North Africa and early European engagements. When they climbed into the Cromwell and opened the throttle, the sensation was entirely alien. The Meteor delivered 600 horsepower. Suddenly, a cruiser tank weighing nearly 28 tons could accelerate like a heavy sports car. On flat ground, a Meteor-powered Cromwell could exceed 40 miles per hour. It was so fast that it practically outran its own chassis. The Christie suspension, a system of large road wheels and long coil springs designed to absorb shocks, struggled to keep the tank stable at those unprecedented speeds, forcing the Army to physically govern the engines to prevent enthusiastic crews from tearing the tracks right off the wheels. For the mechanics in the field, the men working with heavy spanners under canvas tents in the rain, the Meteor was a revelation. It required rigorous maintenance, and its immense size made it difficult to extract from the hull, but it did not inexplicably shatter under load like the old Liberty engines. This was not merely a mechanical convenience, it was a tactical revolution. A Cromwell could not match the thick frontal armor or the devastating main gun of a heavy German Tiger tank, but it no longer had to. The Meteor provided the torque and acceleration to outflank heavier, slower enemies. It allowed British armored formations to cross European battlefields with a speed and reliability that completely altered the pace of their advance following the Normandy landings. The Meteor had solved the immediate crisis of speed and power, but to secure its future, the engine had to leave the Second World War behind and become the heavy industrial heart of the Cold War. When the Second World War ended, the British aviation industry immediately pivoted toward the jet age, leaving piston engines to slowly fade into civilian transport and museum displays. But on the ground, the Meteor was only just beginning its reign. It had proven that a 27-liter cast-iron adaptation of a fighter engine could survive the worst conditions imaginable. The Ministry of Supply had no intention of letting that capability disappear. Instead of shutting down the lines, the rover manufacturing plant at Cox Green in Birmingham kept casting, machining, and assembling the massive V12s. The Meteor transitioned from a desperate wartime fix into the permanent backbone of the Royal Armoured Corps. This was the era when the engine truly achieved scale. It was no longer just powering the Cromwell or the Comet. It was selected to be the heart of Britain's ultimate post-war heavy weapon, the Centurion tank. The Centurion was heavier, more heavily armored, and infinitely more capable than anything Britain had fielded before. It weighed over 50 tons. To move that much mass across broken terrain required an engine that could deliver unrelenting torque without tearing its own internal components to pieces. The rover-built Meteor, now refined and thoroughly divorced from its Rolls-Royce aviation origins, was the only British power plant up to the task. In the years following the war, the sound of the Meteor became the defining noise of British military industry. At tank depots across the country, from the training grounds of Bovington to the transport yards of the Midlands, the earth shook with the deep, concussive rhythm of 27 liters of petrol combustion. The engine, a machine that turns fuel into mechanical motion, was no longer treated as a fragile piece of borrowed aviation technology. It was serviced by mechanics with heavy spanners, covered in thick grease and oil, far removed from the sterile hangars of the Royal Air Force. Rover's engineering teams continued to refine the block. They improved the cooling system, understanding that a 50-ton Centurion operating in the heat of a European summer required massive airflow. They strengthened the cylinder heads, the upper parts of the engine that seal the cylinders, and manage the immense pressure of combustion. The Meteor became so reliable that it allowed the British Army to completely rethink its doctrine. A heavy tank was no longer expected to break down every 100 miles. It was expected to march. A service network, the vast system of manuals, spare parts, and train fitters, grew entirely around the Meteor's unique dimensions. Mechanics who had never seen the inside of an aircraft hangar learned the precise firing order of the great V12. They learned how to extract the massive block from the rear deck of a Centurion using heavy lifting gantries, how to clean the immense carburetors choked with training ground dust, and how to tune the engine by ear. The Meteor demanded respect, but it rewarded that respect with a durability that the old Liberty engines could never have imagined. As the Cold War froze over Europe, the British Army of the Rhine deployed hundreds of Meteor-powered Centurions to West Germany. Across the muddy plains, these massive V12s provided the mechanical deterrent against Soviet armor. The sheer scale of production was staggering. Foundries poured thousands of tons of iron. Machining lines at Rover, and later under subcontracts by companies like Morris Commercial, ran continuously to supply not just complete engines, but the vast network of spare parts, gaskets, valves, and pistons required to keep the fleet running. The British export market also caught the sound. The Centurion was not just a domestic triumph. It became a global export success, sold to allied nations across the world. Every one of those tanks carried a British-built Meteor in the back. The heavy engineering pride of the Midlands was now thundering across foreign deserts and plains, projecting British industrial capability far beyond the island. The Meteor's influence expanded far beyond the muddy testing grounds of Bovington. It became the mechanical foundation for an entire family of heavy military vehicles. When the Royal Electrical and Mechanical Engineers needed a vehicle capable of dragging a damaged 50-ton tank off a battlefield under fire, they built the Centurion Armored Recovery Vehicle. To pull that immense dead weight, they did not look for a new engine. They relied on the Rover-built Meteor. The V12 possessed such overwhelming low-end torque, the twisting, pulling strength of an engine, that it could winch a crippled tank out of a deep trench without stalling. Across the Midlands, the industrial ecosystem supporting this engine reached its absolute peak. Foundries that had once struggled to cast the complex aluminum blocks of the Merlin were now masters of heavy iron. Machine shops in Coventry, Birmingham, and the sprawling Royal Ordnance factories were dedicated entirely to turning out the massive crankshafts, heavy-duty pistons, and thick cylinder heads. The sheer scale of production meant that the engine had created its own massive, self-sustaining industrial economy. A vast service network, the dealers, mechanics, parts suppliers, and manuals that keep a machine running, grew entirely around the Meteor. The official military service manuals for the engine were thick, oil-stained volumes found in every armored depot from Catterick to Aldershot. Mechanics who had never worked on a high-performance vehicle learned the intricacies of synchronizing the Meteor's massive carburetors. They learned to listen to the specific pitch of the exhaust to diagnose a misfiring cylinder. The sound of a Meteor being revved hard in a maintenance bay became a daily ritual, a deafening mechanical symphony that echoed off the corrugated iron roofs of British military workshops. It was in the hands of foreign armies that the Meteor's reputation for unbreakable durability was truly cemented. During the conflicts of the Middle East, particularly in the Sinai Desert and the Golan Heights, exported Centurions operated by foreign armored corps faced conditions that no British engineer at Belper had ever anticipated. The engines ingested fine, abrasive desert sand. They operated in blistering ambient temperatures that pushed the heavy-duty cooling systems, the network of radiators and immense fans designed to regulate the block's temperature, to their absolute limits. Yet the cast-iron V12s continued to run. They ran when lighter, more modern engines from other nations overheated and seized. The Meteor proved that a design born in the freezing air of high-altitude combat could be engineered to survive the most abrasive environments on Earth. This was the era when British heavy engineering commanded absolute global respect. The Meteor was no longer just an engine. It was a physical guarantee. When a crew climbed into a Centurion, they knew that if they pressed the heavy throttle pedal, the 27-liter block would respond. It would vibrate through the thick steel floor plates, emit a deafening, unsilenced roar from the exhaust, and move the machine forward with an unstoppable momentum. In a Britain where an engine could decide whether a heavy armored column advanced across a divided Europe, power was not an abstraction. It was 27 liters of petrol-burning capacity, cast iron, raw heat, deafening sound, and the absolute mechanical trust of the crews sitting inches away from the block. The Rover factory at Cox Green had achieved something remarkable. They had taken a thoroughbred aviation design, a machine that required delicate tuning and high-octane aviation fuel, and battered it into a heavy industrial tool. They had built an engine that was largely immune to the abuse of conscript drivers, the neglect of battlefield mechanics, and the sheer physical trauma of cross-country armored warfare. The Meteor was, by every mechanical measure, a triumph of British adaptation. But that same mechanical triumph carried a fatal flaw. Baked into its very design from the moment W.A. Robotham stripped the supercharger off a crashed Merlin. The Meteor was a petrol engine, an engine that usually uses spark ignition to burn a petrol-air mixture. In the skies, petrol was the only logical fuel for high-performance piston aircraft. On the ground, in the confined, heavily armored hull of a tank, it was a completely different calculation. The V12 had conquered the ground, but the very fuel that gave it life was about to become its greatest liability. The first crack in the Meteor's absolute dominance was almost invisible to the tank crews who trusted it. It did not happen inside the cast-iron cylinder block. It did not happen in the Rover machine shops at Cox Green, where the assembly lines were turning out the most reliable heavy power units in British military history. It happened on the ledgers of military logistics officers. The Meteor did not fail mechanically. It began to fail because of force for, fuel, supply chains, and the changing economics of heavy transport. The V12 was a petrol engine born from an aviation design that required a massive, continuous flow of highly combustible fuel to generate its 600 horsepower. When installed in a 50-ton Centurion tank, the fuel economy was not measured in miles per gallon. It was measured in gallons per mile. Moving a heavy British armored column across a muddy training ground or deploying a regiment across the North German plain during the Cold War required staggering volumes of petrol. A tank is heavily armored, but a tank with an empty fuel tank is just a stationary pillbox. To keep the Meteor-powered Centurions moving, the British Army had to deploy vast convoys of unarmored, thin-skinned fuel lorries, a logistics tail that trailed behind every armored regiment. In a theoretical conflict across Europe, these fuel supply lines would be highly vulnerable. If the lorries could not reach the tanks, the mighty V12s would simply fall silent. The sheer logistical weight of keeping the Meteor fed became a strategic liability. Furthermore, the nature of petrol itself was becoming unacceptable to modern military planners. Petrol is highly volatile. Its fumes gather in the bilges of a tank hull, requiring constant ventilation. In combat, direct hit to a petrol-powered tank often resulted in a catastrophic, instantaneous fire. By the late 1950s, the global military consensus was shifting entirely toward diesel power. A diesel engine, an engine that ignites fuel by compressing air until it becomes hot enough to burn diesel fuel without a spark, offered two massive advantages. Diesel fuel is far less volatile than petrol, drastically reducing the risk of fire under enemy action. Crucially, diesel engines are inherently more fuel efficient, offering a much greater operational range for the same volume of fuel. This was the beginning of Force 6, replacement technology. The Meteor was not being challenged by a better petrol engine. It was being challenged by a fundamental shift in how heavy vehicles were expected to consume energy. NATO was also pushing for standardization across its member forces. The future, according to the Ministry of Defense, was the multi-fuel engine, a power unit that could theoretically run on diesel, aviation fuel, or even low-grade petrol in a desperate wartime scenario. The British military began drafting the requirements for a new, even heavier main battle tank to replace the Centurion. This new machine would become the Chieftain, and it was explicitly ordered that the Chieftain would not be powered by a rover-built Meteor. Instead, the government contracted Leyland Motors to develop a highly complex, opposing piston, two-stroke diesel engine called the L60. The L60 was entirely different from the Meteor. It was supposed to be the modern, efficient, multi-fuel future of British armor. For the workforce at the rover shadow factories and the vast network of foundries and machine shops across the Midlands that had spent a decade mastering the Meteor, the writing was on the wall. The orders for new V12 blocks began to slow down. The massive tooling required to cast the 27-liter iron blocks was gradually reassigned or mothballed. Rover, which had successfully domesticated the heart of a Spitfire, began to shift its heavy industrial focus elsewhere. The paradox of the Meteor's decline was painful for the mechanics and fitters in the motor pools. As the military establishment prepared to abandon the V12, the engine itself had reached its absolute peak of mechanical perfection. Years of incremental improvements had ironed out every fault. A well-maintained Meteor in the back of a late-model Centurion was virtually indestructible. When the first Leyland L60 diesels arrived in the early Chieftain tanks, they were an absolute disaster. The new two-stroke diesels were highly advanced on paper, but in the muddy reality of a tank depot, they overheated, cracked their cylinder liners, and failed with alarming regularity. British tank crews who had grown used to the unwavering reliability of the Meteor found themselves stranded on training grounds, waiting for recovery vehicles, which ironically were still powered by the old rover-built V12s. The military had created a situation where the new technology was fundamentally less reliable than the old technology, but the strategic demand for diesel efficiency was absolute. The state would not turn back to petrol. The Meteor still ran. The Centurions were still deployed in their thousands around the world, but the engine was now officially legacy equipment. It was no longer the future of British heavy engineering. It was simply a stubborn survivor, kept alive by stockpiled parts and mechanics who refused to let the old blocks die. The British Army did not want to lose the Meteor's reliability, but they could no longer afford its appetite, setting the stage for a long, slow retreat from the front line. The retreat of the Meteor was agonizingly slow, prolonged only by the mechanical failures of the diesel engines meant to replace it. Because the new Leyland L60 engines in the Chieftain tanks were so fragile in their early years, the Meteor was forced to stay on duty far longer than the Ministry of Defense had planned. But while the V12s continued to roar across training grounds and in the hulls of armored recovery vehicles, the industrial infrastructure that kept them alive was quietly being dismantled. The ecosystem was collapsing. Rover, having successfully domesticated the aero engine and fulfilled its massive government contracts, was looking toward a different future. The company was investing heavily in civilian gas turbines and the booming market for the Land Rover. The vast Acox Green Shadow factory in Birmingham, the site that had proved British mass manufacturing could tame an aviation masterpiece, was repurposed. The sprawling network of Midlands foundries that had once poured thousands of tons of cast iron to create the 27-liter blocks stopped receiving new military orders. This is how an engine empire truly falls. It does not happen on the battlefield, it happens on the factory floor. When the tooling is scrapped and the casting molds are destroyed, the engine is effectively dead, no matter how many blocks are still running in the field. Force 7, corporate consolidation and brand survival, accelerated the decay. As the British motor industry entered a period of chaotic mergers, eventually collapsing into the monolithic structure of British Leyland, the specialized machine shops and dedicated supply chains that supported legacy military equipment were rationalized, absorbed, or simply shut down. The production of essential spares, gaskets, heavy-duty valves, piston rings, and the massive bearings required for the crankshaft slowed to a halt. For the mechanics of the Royal Electrical and Mechanical Engineers, the Meteor changed from a standard-issue piece of hardware into a logistical nightmare. When a Centurion required an overhaul, a major service process where an engine is taken apart, inspected and rebuilt to operating standards, the fitters could no longer just order a new block from Birmingham. They had to hunt through dusty, dwindling stockpiles in massive military warehouses. They had to cannibalize damaged engines, stripping usable carburetors and oil pumps from dead hulls just to keep the remaining fleet operational. The Meteor had become a mechanical ghost in its own country. It was still widely regarded by the crews as the most reliable heavy power unit in the British motor pool, but it belonged to an era of high-octane petrol logistics that NATO had explicitly outlawed. Ironically, the Meteor's final moments of true operational glory did not happen in British hands. Long after the British Army had committed to diesel, exported Centurions powered by aging Meteors were still fighting in the Middle East and Africa. Foreign armies lacking the budget to constantly upgrade to unproven diesel technology simply kept rebuilding the cast-iron V12s. They pushed the engines far beyond their original design limits, proving one last time that W.A. Robotham's wartime compromise was a work of brutal, enduring genius. But back in Britain, the clock had finally run out. By the time the Chieftain's diesel engine was finally cured of its worst faults, and as even newer platforms like the Challenger took shape, the petrol-guzzling Centurions were systematically withdrawn. The heavy transport lorries stopped delivering the aviation-grade fuel. The oil-stained service manuals were thrown into skips. The mechanics who knew how to tune the massive V12 by ear retired, taking their hard-won sensory knowledge with them. The British military had fundamentally changed the way it moved, and it no longer had space for a cast-iron Spitfire engine. The engine still ran. The fuel logistics tightened. The factory tooling was scrapped. The new diesels took over. The Centurions were retired. The spares ran out. The deafening roar stopped. The ground it held was handed over. The official death of the Rolls-Royce Meteor was quiet, buried under the chaotic restructuring of the British Leyland era and the Ministry of Defense's absolute commitment to the new generation of diesel power. By the time the final petrol-powered Centurions were dragged off the training grounds and replaced by the Chieftain and its problematic Leyland L60 diesels, the industrial machine that had built the mighty V12 no longer existed. The Rover Shadow Factory at a Cox Green in Birmingham, the site that had cast and machined thousands of these massive 27-liter blocks, had moved entirely into the modern era, focusing on the global success of the Land Rover and experimental civilian gas turbines. The specialized foundries in the Midlands that had learned to pour the heavy iron for the Meteor's crankshafts and cylinder heads either closed or were absorbed into larger corporate conglomerates that had no interest in legacy military contracts. But old British engines rarely vanish cleanly, especially ones built to survive artillery fire and decades of neglect. Today, the Meteor survives in a vast, dedicated preservation network. Across Britain, in rural sheds, specialized restoration workshops, and the sprawling halls of the Tank Museum at Bovington, the cast-iron V12s are still kept alive. Private military vehicle collectors and former Royal Electrical and Mechanical Engineers fitters spend thousands of hours and immense sums of money hunting down the last remaining spare parts. They scour auto jumbles and specialist auctions for pristine magnetos, heavy-duty gaskets, and original oil-stained service manuals. Because the military supply chain was shut down decades ago, when massive internal parts cannot be found, they must be machined from scratch by independent specialists. Extracting a 27-liter block from a Centurion hull requires heavy lifting gantries and sheer physical courage. It is not a hobby for the faint-hearted. This preservation is not simply a matter of military nostalgia. A running Meteor engine is a physical argument about a specific moment in British industrial history. It proves that Britain possessed the engineering flexibility to take an elite, highly strung aviation masterpiece, the Merlin, and violently hammer it into a brutal, reliable industrial tool. The Meteor represents a time when the solution to heavy transport was not complex software-controlled powertrains or hybrid efficiency, but sheer unapologetic displacement in low-end torque. It is a monument to an era of absolute mechanical trust, where a tank crew's survival depended directly on cast iron, heavy spanners, and 27 liters of petrol combustion happening inches behind their heads. The legacy of the Meteor is also the legacy of its quiet offshoots, proving just how adaptable W.A. Robotham's original Belper redesign truly was. The surprise footnote to the Meteor story is the Rolls-Royce Meteorite. When the British Army needed to move the 50-ton Centurions across the country, they commissioned the massive Thornycroft Mighty Antar tank transporter. To power this enormous lorry, Rover did not design a new engine. They simply cut 4 cylinders off the Meteor block, creating an 18-liter V8. The Meteorite shared the same unbreakable DNA, the same overhead cam architecture, and the same deafening exhaust note, proving that the basic geometry of the Spitfire's heart could be endlessly adapted for heavy ground haulage. The Meteorite served well into the Cold War, a mechanical sibling that carried the V12's legacy onto the public motorways. Today, the physical sites of this engineering triumph are mostly gone. The Clan Foundry in Belper, where Robotham first ordered the superchargers stripped from crashed aircraft engines to see if the block could survive the dirt, has been swallowed by modern redevelopment. The vast Rover machining lines at a Cox Green, where the Meteor became a mass-produced weapon that saved the Royal Armoured Corps, are silent. The ecosystem of heavy iron casting that supported the engine has largely moved overseas, replaced by global supply chains and lightweight modern manufacturing. The Meteor was never defeated by a lack of engineering brilliance or a failure of mechanical integrity. It was defeated by Force 4 and Force 6, the inescapable logic of fuel logistics, the volatility of high-octane petrol in combat, and the global military shift toward diesel efficiency. It was a perfect machine built for a world that simply could no longer afford to feed it. Yet the sound of that era refuses to disappear completely. To hear a Meteor today is to experience a strange acoustic paradox, because it shares the fundamental firing order, bore, stroke, and internal dimensions of the Merlin. It sounds almost identical to the famous aircraft engine. Spectators at military vehicle shows often look up when they hear it, expecting to see a fighter plane breaking through the clouds. Somewhere on a damp British showground, a preserved Centurion idles on the grass. The massive cast-iron V12 vibrates through the thick steel hull, sending a deafening, familiar roar into the gray sky. A sound waiting for an aircraft that will never arrive. See you in the next video.